Water is captured as surface water. Surface water exists in two different forms. The conventional that most people know and understand is water that is overland flow. That's water that is in lakes, rivers, streams, brooks, creeks. Groundwater, on the other hand, is the water which exists within the earth, within the pores of a rock structure. And these are aquifers. Most of us understand aquifers as the water which we capture that we acquire out of a well. How does water get into the ground, into those aquifers? Well, through infiltration. Infiltration is attained by water penetrating the soil and the subsequent rock beneath it. Infiltration begins as water penetrating that soil and rock, but continues through from that surface through a mechanism of percolation into the rock strata below. So percolation is the physical drawdown of water through soil and rock by gravity. What happens is all of the different void spaces between the particles within the soil and the rock must get filled to 100% capacity. Once they're filled to 100% capacity, then the water within those pore spaces can then move into the pore space directly below it. And it's through this process that water will then percolate, move from higher elevations closer to the surface of the earth through soil layers and through various rock layers, where then eventually it will reside as an aquifer. For the most part, where surface water exists at a particular point in time, at a particular location, comes down to climate. What is the climate like at a particular location is going to dictate how much water there's going to be. So for you and I living in the Ohio, Pennsylvania region, we've got 4 distinct seasons. The spring season, which delivers most of our water through lakes and rivers, comes to us in 2 ways: melted snowpack and through precipitation. That high volume of water that then moves across the surface of the earth through flow through into those rivers and creeks and streams is going to have a punctuated or higher volume of movement during that season, during that spring season. As we move into the summer, rainfall diminishes, we've exhausted most of the spring thaw, and the volume of water is going to reduce. The higher the discharge, or the greater the volume of water, the faster that water is going to then flow. So in high seasons of precipitation and snowmelt, for places like Ohio at mid-latitudes, then the movement of water across the surface of the earth to an ocean basin. In our case, here in this part of Ohio, we're going to move water from the Mahoning Valley into the Ohio River, from the Ohio River into the Mississippi, and then out into the Gulf of Mexico. This time of year in the spring, that's going to move much, much faster. Into the summer, that flow is going to diminish. It's going to take a little bit longer. We see a punctuated or an increased volume of precipitation in the fall. So we're going to be a little bit more rapid getting into that ocean basin. And then winter, water diminishes, and then the volume is going to then take a little bit longer as well. So we've got this variable rate of water moving through river systems based on climate and based on what precipitations are going to take place. For the most part, the global average for a water droplet to move from a high elevation precipitated environment through to the mouth of a river into an ocean basin takes about 10 days. Now, statistics is a funny thing, and we have to remember that there are a lot of variables, particularly in geography, that is going to lead that 10-day period of average questionable, because a lot of rivers, for the most part, are short rivers that exist on the margins of continents. So that water is going to move into that ocean basin much, much, much more rapidly, as opposed to some water falling in Glacier National Park in Montana. It's got to move through all those headwaters out of Glacier National Park into the Milk River, across then into the Missouri River system, from the Missouri into the into the Mississippi drainage basin, and then into the Gulf of Mexico. As a result, that's going to take months and months. So we're going to end up balancing water that takes just a couple of hours through to many months, and a 10-day average doesn't make a lot of sense. The other variable that we need to recognize is that snowpack can stay in place for many years. So if that water falls as snow at a higher elevation, then that volume is not going to make it down the river. Likewise, if that water dropped and was captured at a glacier, it's going to take a whole lot longer as well. So there's a lot there that makes a 10-day statistical average rather erroneous. So with spatial surface water as a temporal relationship to climate, we're going to recognize that dry areas that discharge into oceans and seas are really only going to occur during the rainy season for the most part. A temperate environment at mid-latitudes, those rainy periods are going to happen over more seasons. So we're going to see quicker discharge into those water basins. And that we've got those temporal lags that we mentioned just in the slide before, that the linear distance between the river and its discharge rate is going to depend on how far that water has to travel across a landscape. So illustrated in this map is the Nile River from Lake Victoria through to the Delta. Occupies almost half the length of an entire continent. So we know that the water that is going to move from its source area across, in this case, a couple of different climatic zones, we're going to see a lot of variability in the time it's going to take, or the lag it's going to take from point A to point B, or from the source area through to the end of its discharge area.